one of the simplest and also most abstract.
Beating a professional player of Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try a game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lisa Dong.
A match like no other is about to get underway in South Korea.
At least Nadal is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge. The whole world is watching. Can Lisa Nadal find AlphaGo's weakness? Whoa. Is there in fact a weakness?
The game kind of turned on its axis.
Look at the dice.
That is not confident pace.
It's developing into a very, very dangerous question.
Ooh, hold the phone. Rena's left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, I mean,
It's got to be a career thing.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So that's of course the AlphaGo documentary that just got released. How many of you have seen it already? You did? Wow. I hope it's not pirated, right? So because as far as I know, it hasn't yet shown up in Phoenix area. I think it showed up in LA area for a festival. And I think it just had like a premiere in UK last week. Okay. So the reason we bring up AlphaGo is because we are finally in the last stretch of reinforcement learning, which is when you have large state spaces. Oh my God! When you have large. When you have large state spaces, how do you actually do reinforcement learning, in particular computing the optimal policy? There are a couple of things that AlphaGo winds up doing, including the policy gradient search, which we hopefully get to at the end of the class, and I'll just mention it to you. But in general, this idea of doing the search for reinforcement learning in a parameterized space is a very big part of AlphaGo. In particular, today we will be talking about how to represent value function as a parameterized function of features and weights. All AlphaGo does is the deep part of deep RL winds up being representing that function not as a linear function, but as a neural network. And when we get to neural network right after this, we will notice that neural networks basically can approximate any real valued function. Any real valued function on any variables. There is an existence proof showing that if you just have one hidden layer, we will talk about what the hidden layer is. There's an input, there's an output, there's a hidden layer. If you have one hidden layer, there exists some neural network with a hidden layer that will approximate any arbitrary continuous real value function. And if you have two, then you can approximate also piecewise continuous real value functions. This also actually is the start of a pivot to calculus. As I mentioned, how many of you have looked at the whole partial derivatives, gradient descent. The rest of you, either you're good at gradient descent or you're going to descend to the hell during the class. Because I think you essentially have to remember, you have done this at some point of time, but you haven't used it, but you're going to use it for quite a long time in these classes. That's why I wound up sending that refresher. Okay, so that's basically what is going to happen. By the way, I don't know if you noticed, there was this a nice place where there was a search tree being shown in that trailer. That's Monte Carlo tree search. And actually, we were talking about the fact that DeepMind has this humongous amount of money, and so somebody must have spent a long time making that slide. It's just such a beautiful slide. Just not compared to my slides. It's big, but really that big. And then the guy, of the two people there, the one person that you keep seeing in multiple places is David Silver. He's actually the main architect of AlphaGo. In fact, his thesis research in Alberta with Richard Sutton was in using reinforcement learning for Go. Except at that time, this deep neural networks and how to actually train them hasn't quite happened. So he just basically, when he went to DeepMind, and he's actually one of the first 4 people, the 3 founders, and David Silver happens to be a friend of apparently David Sassabis. And David Sassabis being the main guy. So anyway, I sent you a link to his reinforcement learning lectures in case you want to learn a lot more about reinforcement learning. I will also send another link to what's called the deep reinforcement learning. Basically, the reinforcement learning lectures that David Silver does are, in essence, an elaboration of what I've done here, but slower. So it's like 10 lectures as against 3 lectures. And he only gets to the kind of deep RL, what's become what's known as deep reinforcement learning, only towards the end. And then I'll send you a set of a link to a boot camp that was held in summer on deep reinforcement learning. All of these are essentially a lot of rope to hang yourself. If you want to, you can use it. If not, you don't have to. If you just want to pass this class, as long as you understand what I'm saying, you're fine. Okay, it's in case you're interested in what's going on outside. Okay, so this area is very much in flux right now. There's just a lot of new work that's getting done. For quite a long time it used to be quite somnolent, and now it's become very big. That's part of the reason why I'm actually doing it in the beginning of the course. Okay, so you can hear me. Yeah, good. So as I said, actually, today we're going to look at RL with function approximation, and in essence, it's like a strange way to get into machine learning. As I mentioned a while back, and if you take a normal machine learning course, you will do what's called supervised learning, and if you have some more time, you will do unsupervised learning, and if you have a lot more time than that, then you will do reinforcement learning. As far as I know, in the machine learning class, actually that starts here, reinforcement learning, if at all it gets any play, it gets like last 2 classes or something. But we are actually going to machine learning from the reinforcement learning side. And as I mentioned, in fact, the idea of learning is much bigger than supervised learning. And in fact, you have to understand that by now, we have done a lot of learning. Reinforcement learning is learning, right? And you have done it in atomic state representations. Each state is a black box, okay? It looks as if you didn't generalize in terms of, if I see this kind of states, I should do this. There is no such type of generalization, because each state is S59, S25, S37, S357. There is no structure to the state. Okay. Instead, what we learned is, if there is a good state, S357, and then I've sort of figured out that S25 seems to lead me to S357, by doing some actions, then the value of this state also should be connected to the value of the better state that's coming later. That's the kind of learning you did. You started learning to anticipate that a particular state's value is better than, what its reward is. Okay, so we need that learning, and we now will actually today go into supervised learning part actually, and then we will shift gears and just look at supervised learning as a separate topic, starting probably towards the end of this class and next couple of classes. Okay, and that's where neural networks will come, and that's going to be neural networks is going to be your fourth project. Okay. That's that. So in terms of administrative stuff, actually the midterm is going to be on the week of 10/23. Okay, and it turns out that I won't be here in 10/23 as well as 10/24. I'll have the exam on one of those days. The other class would actually not be. I won't be there. Okay. My default idea is to just have the midterm on 10/23 and no class on 10/25. But I am actually going to take possibly. I'm going to try and see if it is possible to have some sort of a review session by one of the senior grad students on 10/23, and then the exam on 10/25. Would people? So here's the deal, though. If I miss the class, I do want to make up for that class. So you have to give me that time. Okay, whether you like it or not. And so if I were to basically do this review thing, if I can actually get one of my senior grad students to agree to do that, then that doesn't mean that you don't have any makeup class. You will still have a makeup class, okay? Because I'm using one class. And so how many of you would like me to actually explore the possibility of having 10/23 as a review class and 10/25 as an exam? Okay. Okay, so I will try that. And then remember that that's basically just a review class that I'm doing out of the goodness of my heart. Actually out of the goodness of my TS heart. But honestly, we will still have an exam, extra class. Now for the extra class part 2, I have a question. We could either have like a separate extra class, or given that I know that a large number, anytime I actually try to have an extra class, several of you won't be able to come, because I think one of the great stories of ASU is somehow you're all barely here during this exact 1 hour 15 minutes, after that you just completely dispersed and can't be found anywhere else together. But that's the greatness of commuter campuses in general, but the usual, but the point is I could hold a separate class on, like, for example, a Friday, or I could just extend some number of classes to make up for the 1 hour 15 minutes I lose. And the way I would do that would be, starting possibly next class, I will just extend each class by half an hour. And I think if I do it like 2.5 times, then I will be done. Right? Okay. So is there, and then I understand that at 11:55, people who have other classes will leave. I understand. Just try to leave silently. Okay, and the thing will be recorded, and then before the next class, you just see that last part, and then the next class will just continue from where I left off. That's what it's going to be. Okay, so again, there are 2 options. One is doing it this way. The other is having a separate makeup class at some point of time. And if I do it this way, then I will start having it probably next week. So I'm going to have a vote on that. But yes.
Would you alter your office hours if you extended?
Yeah. Actually, in fact, office hours I'm going to make for the next. It's about time that we start. I'm not seeing too many people after the end of the class anyway, so I'm going to just make office hours during afternoons some other times. As I can say, you can still talk to me at the end of the class, but originally I thought that I will actually spend like half an hour, 1 hour talking to people, but even the people who have time will see anyway. So I just have separate office hours for the rest of the session. I'll say that. Yes.
Could you have an extension by starting the class earlier?
Well, that's because you obviously wake up early, but in general, my understanding, and I wake up very, very early, but in general, my understanding is that it will be murder if people are asked to come early instead of late. So I'm just assuming that there will be more. So again, let's ask. So first, extension. How many people are in favor of extending classes versus having a separate, class on one of the Fridays? Extension of the classes. Okay. Does that look like? I mean, so then go down and then how many are preferring a separate Friday class? It looks like the first one is bigger. Right, okay. So that's that. Now, in terms of the extension, how many people prefer extending the suffix versus prefix? How many people are in favor of extending the suffix of the class? Prefix. Wow, there are just lots of people who actually make a money. Well, I mean, so maybe, well, I think it still was the case that suffix was larger, so let me just show you. Okay. Okay, so lots and lots of decisions have been made. So actually then I will just start the attendance and then just say what I just skip those attendance. Okay. I'm just basically, you say yes if you're present. And in fact, you say anything you're present. Okay. That's about that. Are there any questions?
So if we at all possible, it was too much, but to start class 15 minutes early and go 15 minutes longer. For those that have classes, those that have a class that start like at 30 minutes.
Okay, let me just, I can't stop this. I mean, I guess it looked to me, again, let's try it again. How many people are okay with starting 15 minutes early and ending 15 minutes late? That must look like a pretty big number. Okay, so that's what we do. Okay. Okay. Good. I should remember that. Okay, so that's what we do. And if we are I will definitely send another mail. If in fact I'm starting next week onwards, I will send you a mail saying that's what we do. Okay. Any other questions about the exams? One other thing that I should mention is, so in terms of the things that are coming up, you have a reinforcement learning homework that is due end of this week. And the good news is that whatever that homework covers up until that point is what is in the midterm. So the stuff that we're doing, in general, you would have had a chance to do the homework on the material before you go to the that's what we're doing. Okay? And then, so anything else that's not in the homework is essentially kind of not going to be anything else approximately. Okay. Any other questions? Yes?
Will we be getting the solutions for the MDP homework?
Yes, you would. Yeah. Yeah, everything, the solutions will be posted. And in general, part of the issue has been that sometimes people take, as I said, extra time after the deadline, that one of the 3 days, and so we're just trying to avoid posting it. So, then what we're going to do now is the story so far very quickly. Till basically MDPs and reinforcement learning are very closely connected. So you can think of MDPs itself as part of the package. So if you have a known MDP, that means an MDP with the reward and the model known, then we basically compute V star, Q star, and pi star. That's the usual thing. If you compute V star, you can get pi star. And if you compute Q star, you can get V star, from which you can get pi star. Okay, pi being the policy. You can also just evaluate a single policy. We talked about policy evaluation. And the techniques we considered were value iteration for the longest time. In fact, we did 2 types of MDPs, finite versus infinite horizon MDPs. and then we considered value as well as policy iteration. The policy iteration is an interesting thing because there you actually directly started going from one policy to another policy. And as a foreshadowing, in fact, policy gradient method that I mentioned in the beginning briefly today is actually a hill climbing approach, a greedy approach for going from one policy to another policy. In stuff. It's also kind of searches directly in the space of policy. Okay. So then, of course, there's a policy evaluation that we talked about, and then that was considered just MDP, but you can think of that as MDP is when the model is known, and when you have a known MDP, then you can either do model-based or model-free, and if it is model-based, then you just go back there directly. Okay, model-based means essentially you first compute the model, and then it's now a problem it's been reduced to a problem that you already know how to solve. If you compute the model, and if you learn the model through experience, then you can convert it then it becomes a normal MDP, and then you solve it with respect to that. Only difference, of course, is when you are given an MDP by somebody, you didn't have to worry as to whether the model is complete or incomplete. You just assume that the person whoever gave the model to you, they should have cared about whether it's complete or not. Your responsibility is only to make sure that you get a policy that is optimal with respect to the model that's been given. If on the other hand, you're both getting the model as well as computing the policy, you need to make sure that you didn't jump the gun too fast. Okay, so you didn't just basically do a few iterations and get some pretty bad model and then just directly convert it to optimal policy. Because the optimal policy with respect to an incomplete model could be arbitrarily far from an optimal policy with respect to the complete model. Okay, and then of course one very important thing is in the model base, you also actually have to deal with exploration exploitation trade-off. Okay, that's something that you have to deal with. That's why you are in charge of the quality of the model you are learning. And anytime you think you are happy enough, you go back and act as if it's just an argument. Okay. The other idea we looked at is model free. That's what we looked at the end. And there you essentially just skip over the model part. You don't consider learning the transition model. Okay, even though model normally means both transition and reward, typically the big worry people have is the transition model, because in complex, depending on the domain, the transition model can be very large, especially if you have continuous space of actions, for example. And so rather than go through the intermediate point of the transition function, you go directly to the value, and then from the value to policy. Okay, and to go from value to policy, of course, to just get to the value, you do temporal difference learning. Talked about that, which all that says is essentially, if while acting, when you take an action and you find another state, and then the current state's estimate of the current value should be moved towards the value of the neighboring state. Because after all, you are able to take an action from this state and go to that state. So it must be the case that the value of this state is connected to the value of the neighboring state. So that's essentially what temporal difference learning was doing. Okay, and then that's the sort of the policy evaluation aspect of temporal difference learning. Then if you want to compute the optimal policy, then you talked about Q learning, where you still do temporal difference learning, except you essentially consider the Q values. You are updating the Q values rather than updating the value function directly. And then if you do update the Q values, then at any given time, at the end, there is no actual reason to go back to this part, because the Q values already tell you what your policy is. Right? If you know the Q value of a state, then the action you are supposed to do in that state is the action with the highest Q value. That's it. So it becomes a direct way of going from policy, from Q value to policy. There is no additional evaluation needed. So this is all what we discussed. So of course it turns out that Q learning has all sorts of interesting properties. In particular, as I mentioned in the class last time, even if in fact you keep just randomly loitering around the world for long time, then basically do the Q. So when you're doing this, you are updating your Q values, right? At the end of your life of random loitering, whenever you think you had enough of it, at that point, if you ask yourself what is the optimal policy, it will tell you the optimal policy, despite all your loitering. Okay, so that's basically what is meant by saying that Q learning is an off-policy learning. You notice that there is this sort of a chicken and egg problem here, right? I mean, you're trying to compute the optimal policy, and you don't know what the optimal policy is, and so without optimal policy, you don't know how to behave. So in general, one of the worst things you can do possibly is to just keep on behaving randomly for quite a long time, and during that phase, all you're trying to learn is how is the world? What's the layout of the world I'm living in? At some point of time, you think I have learned enough about the world, now I'm just going to figure out my optimal policy. So for the rest of my life, this is why I said in the last class that if you have 2 lives, first life you spend just randomly loitering. And then you die, and the next life you just directly use basically during this random loitering you computed you kept updating the Q values. So the next life you just start using the greedy optimal policy with respect to the current Q values. Okay, so here is so basically that also brings us to an interesting point, which is that there is this notion of regret. Again, I'm just sort of trying to mention this because if you read anything about reinforcement learning, sometimes you hear about algorithms that are regret minimization algorithms. So the regret essentially is what you're basically trying to capture is somebody who sort of very quickly learns the entire model of the world, and then starts using it. Versus somebody who takes a long time to learn the optimal model of the world and start using it. Okay, one of my colleagues once said the following sort of slightly poignant thing, that she always understood the entire course material. It all clicked for her exactly 2 weeks after the entire semester is over. Do you understand what I'm saying? Now, why are you laughing? There are humongous number of bozos in the world where even after 10,000 years after the course, nothing clicks for them. Compared to them, this person is amazingly good, right? Because after 2 weeks after the semester, everything clicks for her. Unfortunately, her GPA is not looking good. Do you see what I'm saying? So in some sense, we do care about how much time you spend in actually getting the model. And so minimizing regret is actually, this is like a second order optimality. It requires optimality in learning to be optimal. Optimality in learning to be optimal. You don't want to waste time just dilly-dally. Okay, it's like the kind of the people in the killer instinct would just say, yeah, just let me know exactly what will be in the exam. That's the only things I'll study. Don't waste my time about AlphaGo documentary and deep reinforcement learning documentaries, etc. I'm just going to study what's required for the exam and I'll get my good grade. I may not want to work with them as my grad students, but they will get a good grade. On the other hand, people who actually spend a lot more time improving their bigger model may not get a good grade because by the end of the semester they may not have known the one question that came in the exam, but they might actually do much better in their life. Okay, but it would be better if you can actually combine both. So in fact, don't just completely go into random exploration. Try to be slightly more focused, and that can be captured by algorithms that do regret minimization. I won't even talk about that right now, but in fact, the closest we can come up to is, remember, rather than just completely acting randomly for a long time and then just in one shot converting it to the policy, I said you could do the following thing, which is, in fact, towards the end of last class, I said that at any given point, with probability P, do what the current greedy policy asks you to do. And probability 1 minus P, do a random action. And in the case of Q learning, this is a very easy thing to do because with probability P, do the action that is the max, that has the max Q value for this state. and probability 1 minus p do any of the actions that you can do in this state. Okay, and if you, for example, so that already is a good thing because it's actually trying to take into account the exploration versus exploitation trade-off. And then you can actually put a schedule on the way that probability is modified. In the beginning, for example, you might put P to be a smaller number. I could say with probability like 0.5, I will do what my greedy policy says, and probability 0.5, I'll toss a coin and do any of the actions. But after living long enough, I make the probability P to be closer to 0.99. So I'm mostly sticking to my learned policy, not exploring any further. Do you guys see what I'm saying? Okay, and the two different schedules, one will have somewhat, the second one will have lesser regret, because in the end you won't think, oh my god, I wasted time watching AlphaGo documentary. That's obviously very helpful to me in long term, but look at my grade. Okay, so basically I would say don't watch the AlphaGo documentary right before the exam. That time you probably should start actually trying to exploit the model. Okay, but on the other hand, on the day one, you say, tell me, what's the first question, second question, third question of the exam? That's another extreme. Okay. So finally, large state spaces. So when a problem has basically, until now we've been looking at tabular representations. Value function is B of S is a value. Okay. Now, one aspect of it is that the table of values is going to be as big as the state space. Okay, even in the context of discrete state spaces, for example, AlphaGo is a discrete state space. I hope you understand that. Okay, there is no continuity. So within the cell, if you move the pieces a little bit within the cell, it looks like a different image, but it's still the same state. Right? There are only a finite number of states for AlphaGo. Okay, finite number of states for chess. On the other hand, there is continuous number of states when, for example, you're doing walking or moving your arms, anything. Any robotic reinforcement learning tends to be continuous state spaces. So, but mostly we look at discrete state spaces, and even discrete state spaces can be very, very large for really large, interesting problems. AlphaGo, for example, Go, for example, is a great case in point. And the second problem is that, so first of all, there is this problem of remembering this such a big table. So one idea is that you want to compress the value. Okay. One idea is that you want to compress so that it would fit in a smaller amount of space. A second idea is that because you're thinking each state is completely different from each other state, you are not actually finding any patterns in the states. So in this Pacman thing, for example, if you, for example, found out that this is a bad state, you won't know anything that